let's try to improve them, improve Wasserstein GAN. The video is online. You can watch it in your spare time. That's actually an assignment. What are we trying to do? We are trying to control the Lipschitz continuity of the functions that we have. So you want to control the Lipschitz continuity. A regular GAN, let's take a closer look at the objective function. You have log of the discriminator, log of 1 minus discriminator. Wasserstein GAN is very simple. It's very similar. You are getting rid of the log and you are getting rid of the sigmoid as the last layer of your neural network, your discriminator. So you get rid of the log, you get rid of the sigmoid. Now you have a function here, which could take any value from negative to positive infinity. That function is going to look at real and generated images, the same way that your discriminator was looking at real and generated images. You get rid of the log, and then this minus sign is going to give you the other minus sign here. So when you're going to code up the idea of Wasserstein GAN, the modifications are minor. You're not going to change much. But you need to make sure that this D function here, the critic, is actually Lipschitz continuous, is one Lipschitz continuous. How would you do that? You copy and paste your objective function here, so you're not changing anything. But at the same time, it turns out that if you control the gradient of your critic, and basically if you control the norm 2 of the gradient of your critic, you're actually making it Lipschitz continuous. If you control it to be less than 1, you're actually helping it to be Lipschitz continuous. Here you can actually use a hinge type of function, or you can be a little bit more relaxed and use a mean squared error as your loss. There is a catch here. This x hat that you see is a convex combination of a real image and a generated image. Because according to the theorem, you need to enforce this gradient penalty almost everywhere. You cannot explore the entire space of images, but rather you can explore the lines between real and fake images. I think I'm going to stop here, and then the discrete version of Wasserstein GAN, or discrete version of a generative process, we are going to cover next session. For those of you who have questions, I'll be around.